Alrighty. So I'm still trying to get caught up on some things. I've, let's see, I've promised a little more video on 4.5. That's sort of behind, but I mean, that is definitely an important section that would be nice to have some video on. I've gotten one video made just on the general introduction to 4.5, but that's all I've gotten to. Yeah, still a reminder, you'll get an exam next, whatever it is, Thursday. Yeah, next Thursday. That will be due Monday. Again, take home. You can use technology and so forth. You just need to document it, and I'll get more out on that stuff. Okay, and I thought today, possibly you need to like strap yourself in and hang on, because if we have time, I'll mention some of the sections we're not really doing anything with, but I think it's worth mentioning them, just so I can, I can say, yes, you've seen it, you've seen that it exists, kind of thing, and in the end, I mean, given you have technology, as long as you understand the basic idea of what the heck a derivative is, and then if you needed to use, say, a hyperbolic cosine function, well, you can look up its derivative, right, or its antiderivative, if that's what you need to do. But you need to know that such things exist, so that's what we'll try to mention toward the end today if we have time. Otherwise, I'll throw it in a video. Questions on any problems? Anything right now? Yes?
I got a question about 5.3, exercise 67.
67 and 5.3. What the heck are they doing there? Verify that f has an inverse, then use the function f and the given real number a to find f inverse prime at a. Okay, hint, see example 5. We'll do that as an example when we hit that, because I thought we'd start with 5.3 today. So, yep. Just if it seems like I'm not going to do that, just throw something at me. Not too hard.
Okay.
Don't use your tennis racket or anything like that. So, anything else? Any other questions on anything? Okay. So yeah, 5.3 inverse functions, and again, I'm not going to go into amazing detail on these, but we do want to hit the calculus parts of all this, and we do want the definition. I think that's good because it does matter. So g of x is the inverse, and I'll go ahead and write function. I'd love to just save that my arm and not write function, but I think it's important because there are lots of different kinds of inverses. There are additive inverses and multiplicative inverses and all that. This is a compositional inverse, so inverse function of f of x when, well, f of g of x, so there's the composition part, just gives you x back for, and this is important, in this definition, for each x in the domain of g, okay, the inside function, okay, and And now, so that's very important. And both of these things have to work. And g of f of x, so composition the other direction, also gets you back to x. And it's for each x in the domain of f. Okay? So we have that, and if we have that sort of thing, we can write g of x as f inverse of x. We could write it that way. We can use that kind of notation. Now, if this is really true, right, well, actually, it's kind of funny in this definition because it's saying g is the inverse of f, and so we can write this sort of thing. Well, but if g is the inverse function of f, then f is the inverse function of g. And so you could just switch those things around because both those compositions have to be true for those domains. And so I wanted to look at how the domains matter. And you know, when you get into inverse trig functions and things like that, often people get lazy and they don't write down domains, including myself, you know, and that kind of, you know, we just kind of go, well, everybody knows the domains are these. But you do have to be careful, certainly at times, with these domain things. So, you know, for instance, as an example, suppose I have, you know, f of x is equal to x squared. Now, we know x squared is defined for all real numbers, and so I'll add that, you know, its domain, x is an element of all real numbers. Okay, because, yeah, we can define x squared for all of those. And then if we let g of x equal the square root of x for x greater than or equal to 0, you know, usually when you think of x squared and square root of x, you go, oh yeah, they're inverses of each other, right? If I take the square root of x squared and that sort of thing, or square the square root, right, I just get back to x. Well, but if you look at these, based on this definition and what I've written here, right, we have f of x, f of g of x, sorry. F of g of x is equal to the square root of x squared, which is x. And that is certainly true for x greater than or equal to 0. And that is g's domain. Okay, so I did the first line, f of g of x. But now, when I do the second line, g of f of x, that is the square root of x squared. And it turns out, right, if I do that, for f's domain here, all real numbers, what happens is I actually get a piecewise defined function. Because really, I'm getting the absolute value of x. And so, the answer here, well, it is indeed x when x is greater than or equal to 0. But you can either write it, since we know x is negative, you could either write it as the absolute value of x or negative x. I'm going to write it as negative x just because that tends to cause people a little panic and you got to think about it a little bit. Okay, so it's minus x when x is less than 0. And so, it doesn't fit our definition. Okay? Because we don't get x back for some of the domain of f. Okay, and so therefore, we would have that g of x is not equal to f inverse of x in this particular case. So g of x is not f inverse of x. Okay? Now, for all practical purposes, sure, if you know what you're doing and the way you're using it and so forth, yeah, it's going to work. But if you've defined things this way, it is not the inverse, these are not inverses of each other. Now, so to make it happen, what we would have to do is define f of x, and we can get that definition from just where did it work here, right? So I look here and I say, well, I need to restrict its domain to make it work, to just get back x. And so I do. I just restrict its domain, x squared for x greater than or equal to 0. And then, g of x equals square root of x. Same domain in this case. They don't have to be, but they are in this case. And so now, g of x is indeed f inverse of x. Okay, so now real quick on notation, right? Functions, we have this one notation that can be problematic, let's go with, how about, let's see, we don't have any Bobs in here, right? No, so we'll go with Bob. If I write Bobs, what does that mean?
Something that belongs to Bob.
Something that belongs to Bob. Maybe. What else could it mean? Could be a contraction for is. Context tells you everything, right? So same thing here, right? Is if I see that, that's 1 over 2. And if I see that, that is, I don't know, what's f? Right? I don't know what it is. It's the inverse function. It's not 1 over. Now, I could really screw things up by using like the function 1 over x or something like that, right? But in general, though, when you see that, I don't know what it is. Okay? And with functions, though, that's the context. If I'm talking about functions, and in particular, either using a general notation like this, or using a function's name, sine, cosine, arcsine, something like that, then that -1 means the inverse function, not 1 over, not a multiplicative reciprocal kind of thing, multiplicative inverse. But, and generally, people in a calculus class don't complain too much about such things. But, just in case you wanted to complain about it, in any language, we use English in here, but in any language, you got stuff like this, where it takes context to actually know what the meaning is. And so you want to think about that context when you're reading stuff. Okay, so paddling, because it would be nice. Today's a beautiful day. It'd be great to be out on a lake or a river or something. Okay, so that's the inverse functions. Now, we have an existence theorem, which also I like to point out, theorem, this is existence of an inverse. This is also important, I think, in a mathematical point of view, because, you know, it really doesn't happen a lot in Calculus 1, but you start getting into Calculus 2 and definitely stuff after that. Math deals a lot with existence of things, like, oh, a solution exists. Okay, I can't tell you what it is, but I know one exists. Right? You know, so that's really different than stuff before Calculus 1. Right? Because before Calculus 1, it is always just, hey, find x. I don't care what else you're doing, just make sure you find x. Right? There's a very concrete answer at the end. You know, here, we're talking about the existence, and so in this theorem it says, you know, f of x has an inverse. Okay, so it has an inverse. Doesn't say what it is, but it has an inverse if, and this is a very typical thing to say in mathematics, if and only if. Okay, and what that means is the implication of this sentence goes both directions. Okay, so in other words, if I know f has an inverse, then I can say this, whatever the next, if and only if f of x is 1 to 1. Okay, 1 to 1, we'll look at that in a minute. Right, now x squared is not 1 to 1. Because if I take 1 squared, I get 1. If I take negative 1 squared, I get 1. If there are two possible y values, other way around. If there's two possible x values that can give you a particular y value, then it's not 1 to 1. So 1 to 1 means if f of x equals f of y, then x equals y. Must be true. That's 1 to 1. Okay, and you take something like x squared, again, it's not 1 to 1 because I could have 1 squared and I could have negative 1 squared. They both give me 1. So f of 1 and f of negative 1 are equal, but it doesn't mean those two numbers are equal that I put in. Okay, so that's one part of the theorem. We know that, so if I know a function's 1 to 1, then I know it has an inverse. And 2 is an equivalent sort of statement is f of x is, strictly monotonic. Okay, so strictly monotonic implies f inverse of x exists. Strictly monotonic, always increasing or always decreasing. We had that's vocabulary from back in like chapter 2 or 3 or something, probably 3. But always increasing or always decreasing. So actually from that then, there are theorems. Theorems are the big statements. But then you can have things called corollaries that are really theorems, but they just sort of follow very quickly from a previous theorem. So we call them a corollary. Okay? It's like, oh, well, once you gave me that big theorem, no big deal to state this other thing. And so a corollary is, in this case then, if f prime of x is strictly greater than 0, or f prime of x is strictly less than 0 for all x in the domain of f. Okay, so if that's the case, then f inverse exists. F inverse of x exists. Okay, and the reason that's a corollary is if f prime of x is strictly positive everywhere that it's defined, then it's monotonic. If it's strictly negative, if the derivative is strictly negative, then it's decreasing everywhere. It's monotonic. It's strictly monotonic. So once I knew this and knew that these derivatives implied the strictly monotonic, oh, okay, I got that one. That was easy. I was looking through the text. I never saw that statement anywhere. I'm not sure why they don't toss that in, but they didn't. Maybe it's in one of the exercises or something like that that is in there. But so, see, these are all about existence. It doesn't tell me anything about what the function actually is, the inverse function, but it tells me there is one. Okay, so then derivatives. So we want to look at the calculus part. Okay, derivative of f inverse of x. Well, it's a chain rule thing, right? So if our function is differentiable, right? If f of x is differentiable, then and we're assuming f inverse exists. Otherwise, I would have no reason to state this. Then for g of x equal f inverse of x, well, what we do is we just use one of our characterizations of having the inverse exist, and we'll go with the f of g of x, right? Then, well, I'll put the punchline up here. G prime of x is equal to 1 over f prime of g of x, like that, okay? As long as f prime of g of x is not equal to 0, because then I would have a problem. Okay. So, as I said, this is just a chain rule, right? Because we take that characterization and we say, well, we know f of g of x has to be x. By definition, right? They're inverses of each other. So this has to work. So now I take the derivative of both sides. Right? So this is a function, that's a function. They're the same function. And so if I take their derivative, that also has to be the same. Well, this side, I don't know what I get. I just have to use the chain rule. And the chain rule says, well, that's f prime of g of x times g prime of x. But this side, I get 1. And see, so there you go. Just divide both sides by f prime of g of x, I've got my theorem. Okay, so g prime of x is 1 over f prime of g of x. Now it's interesting, I don't actually know the answer to this, but I have a feeling that actually this whole thing, this derivation, what it implies is actually if that's 0, right? If that becomes 0 at a particular value of x, my guess is the limit as x goes to that same value here is either plus or minus infinity, and it goes in such a way that the limit of their product is 1. And I'll kind of show you what I mean by taking our x squared and the square root of x again. So if we, let's see, which one am I going with here? I did, oh yeah, so I guess I have f of x is our x squared, x greater than or equal to 0, and g of x is the square root of x, x greater than or equal to 0. All right, so if we look at what happens with that, and I look at f of g of x, that is the square root of x squared, like that. Okay, now if I take that thing's derivative without simplifying first, if I take that thing's derivative, right, we will have f prime of g of x times g prime of x. Well, this is the squaring function is on the outside, so I get 2 times that thing, so the square root of x to the first power. And then the derivative of the square root of x, well, that's x to the 1/2, so bring the 1/2 down, subtract 1, you get negative 1/2. So that derivative is 1 over 2 square root of x. Okay, and notice that does indeed equal 1, right? It is 1, as it should be. But notice what happens, that as this thing, f prime of g of x, as that goes to 0, this goes to positive infinity, but they both go, that goes to 0 and that goes to positive infinity in such a way that the limit of this whole thing, as x goes to 0 from the right, it's the only way it would make sense, but the limit of this thing as x goes to 0 is 1. Right? Because it's 1 for every other value of x, so obviously at 0 the limit must be 1. And so I think that's what happens always, is that if this portion over here goes to 0, the other portion either goes to positive or negative infinity. Now why positive or negative? Well, because, actually I just thought of something, but because this could be negative, right? So if this is negative, this would have to go to negative infinity to get 1. Okay, but actually, this might not have a limit all by itself. And the reason is this could, whatever's here, could actually oscillate back and forth between positive and negative as it goes to 0. And so this would also have to oscillate back and forth kind of between positive and negative infinity in order to make that 1 for a limit. And so this may not have a limit, but it diverges in absolute value, I'm sure, to infinity. But like I say, I'm sure, but I don't know for a fact. Okay, it looks like it would have to be true, but I don't know. Okay, so that's our derivative. So this is nice to know. Okay, so I can possibly use that at times if I need to, but so I have that property for the derivative of the inverse. Any questions on anything? Is that too loud? Bonnie gets pretty loud. I mean, if anybody wants to, you can shut the door. So, but yeah, one time she was here like for hours, and I didn't realize it, and it was really weird, because usually when she gets here, we all know. So, and that's on tape, so you can use it against me. Well, not really tape. It's in the cloud or something like that. Okay. Okay. So this all with the inverse functions and so forth brings us, and so now we're up to 5.4. This brings us to e to the x. So again, I assume everybody's seen e to the x, that function. You've seen exponential functions before. It's certainly part of the prerequisites to be in this course. But the way they introduce it in this particular textbook, it's just kind of interesting because first they introduce the natural logarithm, and they do it with an antiderivative idea, which, it's calculus class. What a great way to do it, and so we get this logarithm as thinking about it like the area under a particular curve, the curve 1 over x, and so now, okay, if we look at the function natural log of x for x strictly greater than 0, so we've defined this function, and we know that f prime of x is 1 over x, and that's for x greater than 0. But notice what that implies. Since x is always positive, f prime of x is strictly greater than 0 for its whole domain, for x greater than 0. F inverse exists. So the natural logarithm function has an inverse. And that's usually how you learn natural logarithm in like a pre-calculus type class, is that, or a college algebra type class or something. They talk about inverse functions, but they introduce e to the x and then tell you its inverse is natural log. Okay, so we define this e to the x thing as y equals e to the x. I did not misspell if. Okay, that is math notation for if and only if. So if and only if x equals the natural log of y. And so there we've defined this function e to the x. Okay, and you say, well, how have we defined? Well, we've said, you give me this pair, and I'll just swap the x in there, the y in there, and now I've got that pair. That will define the function if I do it for enough points. If I do it for all points, there you go. There's my function. And, technically, we've got that notation there. It makes it look like it's an exponential function. but there's nothing there that says it really is. It's just a notation. Okay, it's just what we use. Now, though, I just thought I'll just do one of the properties, right? So remember with exponential functions, if I have two bases and I have, b to the x times b to the y, that, an exponential function like that, that's b to the x plus y. That's a nice property of exponential functions. Well, okay, so let's look at if, so g of x is f inverse of x here. So it's the inverse of the natural log function. Now, if I look at g of, say, I'm going to use an a and a b as opposed to the x and the y. So suppose I look at g of a times g of b. So you see I'm trying to do this, right? And what I want to show is that g of a times g of b is the same as g of a plus b. Okay? Because that is what that's saying. Is that if I had some other function h, h of x times h of y is h of x plus y. So that's what I'm trying to show. Well, I'm going to use my inverse functions. And this is a big composition, but this is g of the natural log of g of a times g of b, like that. Okay? Right? Because what I did was I took the natural log of this number, whatever it is, and then I took the inverse of the natural log using g, and so that should get me back to that. Okay, so I just did the inverse of g, but then did g as the inverse of that function. And so, let's see. So then this is g of, well, natural log of a product, we already have that property, right? That is the natural log of g of a plus the natural log of g of b. And now I use the inverse property of log and g. Natural log of g of a is a. Natural log of g of b is b. And so this becomes g of a plus b. Starting to look like an exponential function. Okay, and the other property, b to the x all to the power p, right? You just multiply the exponents, you get b to the px. You do the same sort of thing here. You do it with g of a to some power p. Take take g of the log and use the properties of the log, and you get that property that way. So, yeah, this makes sense. Exponential function. Yep. It has the properties of an exponential function. And let's see. So, yeah, and so you can get to, what is the value of e? If that's just an exponential function, then e must be some real number. And, well, what would you do? Well, I guess what you'd have to do is, if you're asking what the heck does e equal, again, I might use something like this. Natural log of e to the 1 is 1. Has to be. Inverse functions. And so what it means is e is equal to x such that natural log of x is equal to 1. So you would have to mess with the natural log function to try to find that x value. Right? I mean, you think of something like decimals. You get it to plot for lots and lots of different values. Try to figure out where it's 1, has a y value of 1, what's that x value. And, and we find that what e is, around 2.71828, 1828, I think. And it's great that way, right? Because it looks like it's just going to repeat. But it doesn't. I think the next digit's like 5 or something. I don't know. So it gets you all excited and then, no. Yeah. So it's a transcendental number. It's like pi. It never repeats. Okay, so E around 2.7, 2.719, or 18, I guess, 2.718. Okay, so there's E. And now, since we're in our calculus class, pretty much we need to know its derivative, and then I guess once we know its derivative, then we can do antiderivatives or something with it as well, maybe. And let's see. Well, we have g prime of x. We know by our theorem is f prime of g of x. Okay? So remember, f is natural log, right? So we have, I'll just put down here, f prime of x is 1 over x, because that's the derivative of the natural log. And so this is equal to 1 over g of x, which is equal to g of x. Awesome. So that says the derivative of e to the x with respect to x is e to the x. Now that is my kind of function. Now, because of that, then, the antiderivative is mighty darn simple, right? Because, the derivative of this function is just that function, so the antiderivative of e to the x dx is just e to the x plus an arbitrary constant. So I like that function. And then, now, suppose you have something like, y equals e to the kx. Then taking that derivative, we get y prime is equal to, well, the derivative of e to something is e to that something. Okay, so it's a chain rule, right, because we have e to the whatever that function is up there. So that's e to whatever that function is up there times the derivative of that function. Kx, derivative of kx is k. So times k. So another way you could write this is, it looks a lot like implicit differentiation when you write it that way. But right, y prime is just k times y. Okay, because that's y, e to the kx. So we've got y prime is k times y. And the reason I point that out is that is a very, very well-used differential equation model. Okay, for growth. Lots and lots of things. So think about it. It says the growth rate of something is proportional to how much of that something is there. That's what that says. Oh, bacteria. How fast is it going to grow? How much is there? Right? And so bacteria, you need to know what K is, but bacteria. People. COVID-19. You know, because it's all a growth of something. And so you can even look at things as they spread through populations. And so a lot of epidemiology has a lot of exponential models. So, so here, you know, here's an exponential model for something in terms of derivatives. So if the growth rate of a population, whatever that might mean, whatever you're talking about for a population, if that growth rate seems to be proportional to how many are there, oh, it probably behaves as an exponential function. Okay, questions at this point on anything? No? Okay. So yeah, if we do another, say a definite integral with an exponential function. So for instance, suppose I want to do the definite integral from 0 to 1 of e to the 2x plus 1 dx. Well, what I want to do is, I see a chain rule opportunity here because I see e to something that's more complicated than x. And so I'll try u equals 2x plus 1, in which case my differential u is 2 dx. So I'll put the 2 in there and take out a 1/2. So I'll have 1/2 the integral from 0 to 1 of e to the 2x plus 1 times 2 dx. And now it's ready for my substitution. So I get 1/2. I'll get an antiderivative here. Now that's just e to the u, and the 2x dx is my du. Now remember on definite integrals to change the bounds. So I went from x equals 0, so that's now u equal 1. And then x equal 1 is u equal 3. Okay, so I have to make those substitutions as well. But now I'm ready to just do my antiderivative, which is just 1/2 e to the u. That's nice. From 1 to 3. And so I get 1/2 e cubed minus e, or e to the 1. And whatever the heck that is. Put that in a calculator if I need a decimal equivalent. Okay, any questions on that? Okay. Well, I think I'll at least be able to mention other bases, probably not the trig functions, but so other bases for logarithms and exponentials. Now in math, unless you are teaching like math for elementary school teachers, which often will use like base 5, but generally, the bases that mathematicians or engineers or somebody like that would use, they would look at 2, 8, 10, and 16. Okay, base 2, because that's binary and computers are binary. Base 8, again, because of computers. Base 10, because it's how we count. And base 16, again, because of computers, hexadecimal stuff and all that. And so those are the other bases. And, we have something like, our definition, y equals 2 to the x, if and only if log base 2 of y is equal to x, and so on for the others. Okay, and so now, if I want the derivative of some base, and so it doesn't have to be 2, 8, 10, or 16, it could be any base. But if I want that derivative, that exponential function, it's almost the same idea. It's the natural log of b, so natural log of the base times b to the x. So it's the b to the x, right? You just get back the b to the x, but the difference is I've got natural log of the base. Well, if the base is e, natural log of e is 1. So it disappears from view. Okay, and then similarly, if you want the derivative of a log base b of something, like that, then same idea, right? We should get 1 over x. Well, like the natural log. Well, it's not quite 1 over x. It's 1 over the natural log of b times x. And again, if b happens to be e, then that makes a 1 and disappears. Okay, so that's that's all that's happening with other bases is, unless you want to worry about the algebraic part of it, from the calculus point of view, you just need to realize that the rules are almost the same, and they collapse to being the same when b is an e. But yeah, they're slightly more complicated. And so you have to worry about that with derivatives and antiderivatives. But we're not going to really worry about derivatives of other bases, that kind of thing. Okay? All right. But you can always look them up if you had to, right? And that's all that's going on. All righty. And so I will keep working diligently and see if I can catch up to anything. And see you all on Monday.